Tonight, we are traveling to a young star system where a giant world remained hidden in plain sight. NASA's James Webb Space Telescope has revealed a planet buried inside the glare and dust of Beta Pictoris, one of the most famous laboratories for studying how planetary systems are born. The discovery is a reminder that even the best-known stars can still keep extraordinary secrets. Beta Pictoris lies roughly 63 light-years away in the constellation Pictor. In cosmic terms, that is our neighborhood, but the system is only about 24 million years old, a newborn compared with the Sun's age of 4.5 billion years. Around this brilliant young star, astronomers see a broad disk of dust and debris, the raw material left over from the construction of planets. For decades, Beta Pictoris has been a kind of time machine. Its disk is tilted almost edge-on from our perspective, making the structure easier to study, while its brightness has allowed several generations of telescopes to watch the system change. Scientists have already detected a prominent planet, Beta Pictoris b, orbiting far from the star on a path that takes about 22 years. But the inner system was much more difficult. Close to the star, reflected light from dust and the star itself can overwhelm the faint glow of a planet. This is the central challenge of direct imaging. A planet may be enormous, hot, and young, yet still appear like a candle beside a searchlight. The James Webb Space Telescope was designed to work in exactly this kind of darkness. Its mirror collects infrared light, the longer wavelengths emitted strongly by warm young planets. Webb also carries coronagraphs, instruments that block much of a star's light so that nearby objects can be separated from the glare. Using Webb's high-contrast imaging capabilities, researchers identified a second giant planet, known as Beta Pictoris c, much closer to its star than the previously known world. The planet had already been inferred indirectly through the gravitational wobble it produced in its star, but Webb provided a direct look at the planet's own infrared emission. That distinction matters. Indirect methods tell us that something is pulling on a star. Direct imaging lets astronomers begin to measure the object itself, its temperature, brightness, atmospheric chemistry, and perhaps even the way it formed. In Beta Pictoris, these two approaches finally meet, turning an invisible influence into a physical world. Beta Pictoris c is a gas giant, several times more massive than Jupiter, orbiting at a distance comparable to the region between the asteroid belt and the orbit of Saturn in our solar system. Yet the comparison is imperfect, because this planet is still glowing with the heat of its recent formation. Young giant planets are not cold, quiet spheres, they are leftover embers of the process that built them. The new observations also tell a story about timing. Because the system is so young, its planets are still moving through a disk crowded with dust, planetesimals, and fragments. Collisions may be common. Gravitational interactions may reshape the disk. The architecture we see is not a finished monument, but a planetary system caught in mid-construction. Imagine watching the solar system during its first few tens of millions of years. The Earth would not yet be the calm blue world we know. The planets would be gathering mass, scattering debris, and competing for stable orbits. Beta Pictoris gives astronomers a rare opportunity to see that violent and creative era happening around another star. The discovery is especially valuable because Beta Pictoris c may be very different from Beta Pictoris b, even though both orbit the same star. One planet lies farther out and completes a long journey around the system. The other occupies the inner region, where the disk is brighter, hotter, and more dynamically complicated. Comparing the two worlds could reveal whether they formed in the same way. Did they grow slowly from a solid core that captured gas, like the leading model for Jupiter? Or did parts of the disk collapse rapidly under their own gravity? Their masses, temperatures, and atmospheric compositions may preserve clues to those competing origins. This is one reason astronomers care about planets that are too young to resemble Earth. They are not necessarily candidates for life, but they are natural experiments. Their atmospheres retain heat from formation, their interiors are still settling, and their orbital arrangement records the early gravitational negotiations that shaped the system. Webb's infrared vision is crucial because the planet's light is not mainly starlight bouncing off a surface. It is heat. A newly formed giant planet can shine in infrared wavelengths, while remaining nearly invisible in ordinary visible light. By splitting that light into a spectrum, scientists can search for signatures of molecules such as water vapor, carbon monoxide, methane, and clouds made of silicates or iron. There is another layer to the discovery. Beta Pictoris has been observed for so long that its system is often treated as familiar. The star appears in textbooks, research archives, and images of young planetary disks. But familiarity can create a dangerous illusion, the belief that a well-studied place has nothing left to reveal. Webb repeatedly challenges that illusion. Its sharp infrared vision does not simply produce prettier pictures. It changes what counts as observable. Objects that were previously only statistical signals, gravitational hints, or hidden behind dust can become individual targets with measurable light. The hidden planet also shows why astronomy is rarely a single observation story. Detection requires a chain of evidence, earlier measurements of the star's motion, careful modeling of possible orbits, suppression of the star's glare, and repeated checks that the faint source is truly moving with the system rather than being a distant background object. Every step protects against a different mistake. A wobble can be misread if stellar activity imitates a planetary signal. A faint point can be a background star. A processing artifact can look convincing until it disappears in another dataset. Confidence grows when independent methods converge on the same explanation. For viewers, the phrase, "a planet hiding in a famous system," may sound almost mysterious. Scientifically, the hiding place is more precise. The planet was concealed by contrast, distance, and geometry. The star was not merely bright, its light was concentrated into the same tiny region where the planet's signal needed to be found. This is a recurring theme in the search for other worlds. We do not usually fail to see planets because they are absent. We fail because the universe presents them beside something much brighter. Finding them requires instruments that can distinguish a whisper from a shout without destroying the whisper in the process. Beta Pictoris C is also a lesson in scale. Light from the system takes decades to reach Webb, and the planet's orbit takes years to unfold. When astronomers compare observations made at different times, they are not just making a movie. They are assembling a slow-motion record of a world moving through its orbit, while seeing each frame from a different moment in history. Even the planet's distance from its star has a familiar but unsettling meaning. If placed in our solar system, it would orbit in a region where the sun's light is weaker than on Earth, yet it would still radiate strongly because its internal heat has not faded. The planet is a furnace left over from birth, cooling across millions and eventually billions of years. As it cools, its brightness will decline. A future civilization observing Beta Pictoris might find the same planet far harder to image directly. The window of easy infrared visibility is temporary, which makes our observation of it especially fortunate. We are seeing the system during one of its most informative phases. The disk itself may be shaped by these planets. Gaps, warps, clumps, and asymmetric clouds of dust can be fingerprints of gravitational sculpting. A planet moving through the disk can shepherd smaller bodies, scatter debris, or clear a lane around its orbit. The architecture surrounding Beta Pictoris is therefore not background decoration, it may be evidence of the planets at work. Researchers will now ask how the two giant planets interact. Their orbits may remain comfortably separated, or ancient gravitational encounters may have moved them into their present configuration. The outer planet's path and the inner planet's path could reveal whether the system formed quietly or experienced a dramatic rearrangement. Those questions connect one distant star to a much bigger problem. Planetary systems are common, but their shapes vary enormously. Some pack several planets close to their star. Some contain hot Jupiters that orbit in days. Others may have distant giants, scattered debris, and small worlds hidden in the shadows. Our own solar system is only one example, not a universal template. By studying Beta Pictoris while it is young and bright, astronomers can test which features are temporary stages and which may become permanent. They can compare a system in progress with the mature system that surrounds us. The result is more than a new dot in a telescope image. It is a new calibration point for theories of planet formation. Models must explain not just that giant planets exist, but how multiple giants can emerge early, survive in a dusty disk, and occupy stable orbits while the system is still changing. And there is a human dimension to this discovery. The planet was not found by simply pointing a telescope at the sky and waiting for a miracle. It emerged from decades of patient observation, improved detectors, mathematical predictions, and engineers learning how to make a space telescope hold its gaze with extraordinary precision. That patience changes the way we understand new discoveries. The planet itself is ancient by human standards, but the knowledge of it is new. Its light crossed interstellar space long before our species could build cities, and only now has that faint signal become part of our shared map of the universe. When you look up at the night sky, Beta Pictoris appears as a star too faint to notice without equipment. Yet around it, worlds are being assembled in darkness. One of them has now stepped out from behind the glare, not because it became brighter, but because our instruments became clever enough to recognize its quiet heat. The James Webb Space Telescope has not finished exploring this system. Future observations may refine the planet's mass, identify molecules in its atmosphere, measure its temperature more precisely, and track its orbital motion. The disk may reveal additional structures, and other planets may still be waiting closer to the star or farther out. That possibility is the most exciting part. The famous system is not closed, it is open to revision. Every better observation can turn an assumption into a measurement, a hint into a world, and a familiar star into a new frontier. So Beta Pictoris leaves us with a simple cosmic warning: the universe can hide its most important evidence in the brightest places. Around a young star, inside a cloud of dust, a giant planet waited for the right eyes to find it. And somewhere in the darkness beyond it, there may be another world still waiting. Not silent, not empty, and not absent, only concealed by the limits of what we have learned to see.